welcome to the last presentation of today's webinar. My name is Konstantin Keil from the Justus Liebig University, and I'll talk a little bit about what we're doing at the university and what is our part in the GIESEPP MP project and so on. So let's start right into it. First of all, with who we are. So the Justus Liebig University in Gießen, as the name implies, is located in Gießen. You can see it here on the map. This is almost in the middle of Germany. And just to give you some key facts about the university, it was founded 1607, which means there's a lot of history is passing since then. And this is also the reason why this university is spread all around the whole city of Gießen. And it's a quite a big university with almost 27,000 students. And also a city with one of the highest student densities in Germany. And as a full university, there are many topics you can study, like medicine, psychology, and economics. But for now and for this presentation, let us focus on physics and especially electric propulsion. And basically, you can't say electric propulsion and Gießen not without naming Professor Horst Loeb. You can see him here on this picture on the left, because he is the inventor of the radio frequency Einthruster, the RIT technology in the 60s. And as you already heard in the other presentations today, this RIT principle is the principle also of the RIT2X, which is the main topic of the GIESEPP MP project. And at the Einthrusters working group here in Gießen, we're not concentrating only on the radio frequency Einthruster itself. We're also doing scientific research all around electric propulsion, which means, for example, that we also focus on the search for alternative propellants, like here iodine instead of xenon. We are developing diagnostics to better understand the thrusters or to measure certain parameters of the thrusters. We're also developing neutralizers. As you already also heard today, this is a component that is needed together with the thruster, because we expel positive ions with the thruster. And without a neutralizer, which emits electrons, a satellite would charge up. And so you need a neutralizer. Another hot topic nowadays is the EMC, electromagnetic compatibility, which we're focusing nowadays our scientific research. And of course, we're doing a lot of simulation all around the Einthrusters here in Gießen. So that was just a quick summary of who we are. But now, what exactly is the task of the university in the GIESEPP MP project? And these are basically two parts. One part is the scientific support, because of our background and our long heritage in this field. And on the other hand, we're helping with tests and give access to our test facilities. So let's have a look at test facilities and the space simulation in general. So first of all, if you want to test a thruster and also want to be sure it's a reliable thruster and a reliable satellite system, you have to keep in mind what kind of environment you're facing in space. And here are some bullet points that summarize this very rough ambient environment. First of all, I think this is clear that we have a vacuum all around the thruster in space. But the next point, for example, the solar radiation can cause problems. As for example, 1 Earth distance away from Sun, you have a power flux density of almost or around 1.3 kilowatts per square meter, which is a lot. So if you don't have a good thermal management, you can quickly get very high temperatures, which can cause problems. We also have other kinds of radiations coming from the cosmic background radiation, like X-rays, gamma rays, and particle radiation, which is a topic which is mostly or very important for the electronics that have to withstand these radiation types. We also have a cold background, so the parts of the thruster in the satellite that don't directly face the sun are looking at the cold space, and then you have a completely different situation with very, very low temperatures. Another point is atmospheric drag, which may seem a bit counterintuitive compared with the first point, the vacuum. But for example, in the low Earth orbit, where, for example, the ISS is situated, you still have a measurable and recognizable atmospheric drag that can, if you don't compensate it with a thruster, can cause a satellite to crash on Earth back again. And another topic which is emerging in the last years and gains more importance is micrometeorites and space debris, which means that from satellite collisions and things like that, we have particles and material chunks in space that travel with very high velocities around and can damage your thruster or satellite by impact. But for now, and especially our space simulations here in Giessen, let us focus now mainly on the vacuum side, because this is most important for the operation of the thruster, to have it in a vacuum condition. So how do you set up this vacuum situation for the thruster? So first of all, you need a chamber, a vacuum tank, where you can put into the thruster and use a pumping system to get rid of all the air that is in this vacuum chamber. But that's not all that you need to operate the thruster for tests. You also need some kind of test power supply, so voltage sources to apply voltages to the grid system of the thruster, or to deliver the current for the coil of the thruster, because we are talking here about electric propulsion. And you need also some kind of propellant. In most cases, this is xenon. And then you need also a flow control unit to precisely insert defined amounts of propellant into your thruster. And maybe you also want to control this all together with a PC, so you have access to all the control parameters and can log all the parameters and have a nice and easy access to the operation. And inside the vacuum chamber, you need some additional hardware, like, for example, diagnostics or a beam dump for the ion beam that comes out of the thruster. So this is a simple sketch of what you need as a minimum to operate a thruster. Let's have a look at a real example here at the university. For this, I want to show you the Jumbo. This has its name because, as it was commissioned in the 60s or 70 years, around that time, it was one of the largest vacuum facilities in Europe, with a volume of around 30 cubic meters. And it can reach a base pressure of almost 10 to the -6 Pascal. And to reach this pressure, you need lots of pumps. You can see here on the right. And all kinds of different types of pumps, roughing pumps, turbomolecular pumps, and cryopumps. And all these test facilities here are operated by students and PhD students. So that's one of one part of the daily business we're doing here. So, and of course, we have some other facilities for different occasions or general purposes like here, or for neutralizers, for alternative propellants like iodine, and for the EMC topics. So that's what I wanted to say about the test facilities. But now back to the topic in the GIESEPP MP project, what we're here doing for this project. And for that, I have taken out some examples that I think are the most interesting parts, because all this whole topic, what we're here doing around this project, is very versatile and fills a long list, and I show you some examples. So first of all, going back to the test infrastructure and the test facilities, if you have the test power supply, for example, in your laboratory, you also need to somehow control it. And what we're doing is then to write a software to be able to control all these voltage sources, to switch them on and off, to monitor them, to measure all the parameters of the thruster, write them in log files, and also to be able to handle special cases of the thruster, some kind of operation failures, and to bring it back to a safe operation point. So this is basically programming tasks that we're doing here, but we're also concentrating on scientific research, especially in the sense of diagnostics and to improve the diagnostics. So I have here an example. One of my colleagues built and measured with it. It's a neutral flux probe. Neutral flux probe, this is a device with which we can measure the neutral flux that comes out of the thruster. So you can see here, this is this device, and this is the thruster. And by measuring the neutral flux, or the unused propellant, if you wanted to say it so, one can get inside of the thruster how efficient it works, and get an idea of the situation inside the thruster. So if you do this measurement, you get a spatially resolved measurement of the particle flux, and then you can see here on this picture that you can see where this particle flux comes mostly out of the thruster, and how it distributes in the space in the vacuum chamber. Quite similar device is a Faraday array, but with the Faraday array, we don't measure the neutral flux or the neutral particles that come out of the thruster. With it, we measure the ions that come out of the thruster. So you can see here the thruster and this device. And here you can see the measuring result of this. And then with it, you can get an idea how broad the ion beam is that comes out of the thruster. And that's also very important to know about your thruster, because you want a very parallel beam out of your thruster, and not something that has a big diverging angle. And it helps also to improve the thruster if you know how the beam comes out of it. Yeah, and we want to take, within this GIESEPP MP project, we want to take these kinds of diagnostics. And another student here builds a travel unit on which we can put all these diagnostics I showed you. And we want to measure very near to the thruster. So we want to have the hope that by measuring in the near field of the thruster, to get more insight into the thruster, to know which plasma conditions we have in a thruster, and maybe can gain some insights how you can improve this whole system. And last but not least, I want to do some work about the modeling of the thruster, which is a part I'm mostly working on. But first of all, let me answer the question, why doing modeling? I mean, in principle, you could just build your thruster, measure it, and see if it fulfills your requirements, and then everything is fine. But with the modeling and by choosing the physical phenomena you need to describe the situation you can find in the experiment, one gets a better understanding of the overall system. And if you have this better understanding, you're able to make some predictions about the system. And you're also able to measure quantities that are normally very difficult to measure inside the thruster. And in the last step, if you have set up a good working model, you can easily change some parameters of the thruster and see how then the system behaves, and you are able to improve your system very easily without building every time a new thruster, which can save money and also time. So let's have a look at an example of the modeling. For this, I want to talk a little bit about the grid erosion, which is very important topic of a thruster. Grid erosion means, let's have a look here at this picture. Shown here is just one single extraction hole of the grid system. You also already saw today this whole grid system. We're just looking at one hole with here the axis of symmetry. And you have here your ion beam that gets extracted out of the plasma here into free space. And sometimes it can occur that a slow xenon ion is created here in this region from a process called charge exchange. And these slow xenon ions are attracted to the negatively biased acceleration grid. And when they hit here this grid, they take a little part out of the material. They sputter the material on impact. And if you operate a satellite over several years, this little damaging can accumulate and cause a widening of the grid holes, which causes a drastic reduction in the efficiency of the thruster. So one want to predict this phenomena and maybe get an idea how you can improve that this damage doesn't occur. And for this, we set up a model that consists out of several submodels describing different physical phenomena, like the ion interaction with the electric field or the neutral gas that travels here through this grid system. And if we take all this together, then we can have a look here at the results. I have here as an example a grid system from a NASA thruster that was run for several thousand hours. And you can see here on the picture that these holes get wider. And you also have here these darker and brighter spots on the grid system. And with the modeling, we're able to predict this widening of the holes and also where these darker and brighter spots come. And I think that's a nice result to be able to see that it fits with the experiment. And the next step would then within the GIESEPP MP project to do a statement on the quantity of this erosion, and then in the near future maybe to have an insight how to improve or to avoid this effect. And that was a very brief summary of all the topics we're doing here in Gießen. I want to thank you still for your attention here at the last presentation. And I think we're all here, all the other presenters as well, for your questions at the end. Thank you.